So if we look here at pyrimidine synthesis, we'll first notice that in contrast to purine synthesis, the pyrimidine base structures are synthesized before the addition of the ribose sugar. You can see that it's several steps into the synthesis before we add our activated 5-carbon sugar, PRPP. So the initial step in the pathway involves a reaction catalyzed by our regulatory enzyme, and that's carbamyl phosphate synthetase 2. And this is a cytosolic enzyme that catalyzes a similar reaction to the enzyme carbamyl phosphate synthetase 1, which is mitochondrial and part of the urea cycle. So this is also our regulatory step for the pathway, and it results in the synthesis of carbamyl phosphate. Similar to purine synthesis, from here we go through a series of additional reactions until we converge on a common intermediate, and for pyrimidine synthesis, that's UMP. I also want to draw your attention to the intermediate orotic acid. We've also seen this as orotate, and we've seen accumulations of orotate as part of urea cycle deficiencies. If you remember, urea cycle deficiencies, which resulted in an accumulation of carbamyl phosphate, could result in the presentation of the individual having elevated levels of orotate or orotic acid. And that's because the excess carbamyl phosphate from the urea cycle was shunted to our cytosolic pathway seen here, and the additional carbamyl phosphate increased flux through pyrimidine synthesis. What's also noted is that pyrimidine synthesis deficiencies can also be characteristic of orotic acid. So a deficiency in our enzyme here, orotate phosphoribosyl transferase, would also result in an elevation of orotic acid or high levels of orotate. However, in the case of an enzymatic deficiency here in pyrimidine synthesis, we would not see an elevation of ammonia. And that would be a key way of distinguishing between deficiencies here in pyrimidine synthesis or in the urea cycle. So once we've generated UMP, it can undergo phosphorylation to UDP and subsequent UTP, which can be converted into cytidine triphosphate. Alternatively, this UDP can undergo a reaction with our enzyme, the ribonucleotide reductase. And this enzyme will convert our UDP into the deoxyuridine diphosphate form. From here, our DUMP can be converted into thymidine monophosphate using the enzyme thymidylate synthase, as well as a carbon donor from the folate cycle. So the synthesis of DTMP for DNA synthesis is our rate-limiting step for the replication process. And we'll see in subsequent slides how inhibition of either the folate cycle or the enzyme directly can reduce production of nucleotides for DNA synthesis. So in contrast to purine synthesis, pyrimidine degradation is metabolically favorable. What I want you to take home from this figure is that we can metabolize pyrimidines into intermediates that we can metabolize through our common pathways we've already discussed. And this is not the case for purine degradation, and so we'll talk about purine degradation in our final piece of this week. And finally, this figure summarizes the interconnected regulation of both purine and pyrimidine metabolism. Our enzyme here, remember, is carbamyl phosphate synthetase 2, and you'll notice that it's regulated in several manners. First, it's allosterically activated by high levels of our activated sugar, PRPP, and it's inhibited by high levels of purine nucleotides. It's also inhibited by high levels of the intermediate UTP. So this regulation of our enzyme carbamyl phosphate synthetase 2 is the most important to focus on here. And note that it's regulated both by pyrimidine as well as purine nucleotides. So as I mentioned previously, there's a couple inhibitors of pyrimidine synthesis to be aware of, and they have specific clinical relevance. One is 5-fluorouracil, and this is a nucleotide analog. And it will inhibit the reaction catalyzed by thymidylate synthase, which converts DUMP into DTMP. And so the reduction in the synthesis of our DTMP reduces the amount available for DNA replication and is therefore effective at inhibiting proliferative processes, such as in the case of cancer replication. Methotrexate is an additional inhibitor, and this inhibits the folate cycle. The direct location of inhibition is at the dihydrofolate reductase enzyme. And we know that folate is required for this conversion. So again, by inhibiting the folate cycle, you inhibit the conversion of DUMP to DTMP. And therefore, it's also effective at reducing the ability of the cell to proliferate by reducing DNA replication. So we're going to finish this week by looking at the interconnection between purine-pyrimidine synthesis as well as the folate cycle to help us get a better idea of how these inhibitors impact the process. So if we start here with pyrimidine synthesis, we have our substrates and our regulatory enzyme carbamyl phosphate synthetase 2, and this will generate carbamyl phosphate. From orotate, we then add our 5-carbon activated sugar, PRPP, to generate uridine monophosphate, or UMP. From here, we can undergo phosphorylation to UTP and conversion to cytidine triphosphate. Or we can convert UDP to the deoxy form, again using the ribonucleotide reductase. We dephosphorylate it to the monosphosphate form, DUMP, and then this is converted by thymidylate synthase to generate DTMP. And again, this is required for DNA synthesis. Uracil is not incorporated into DNA. So we also need folate, an intermediate of the folate cycle, as part of this conversion. So for purine synthesis, we start with our activated 5-carbon sugar and generate 5-phosphoribosylamine. Our regulatory enzyme, again, is responsible for this conversion. We generate the intermediate inosine monophosphate, which can then be diverted to AMP and GMP. So the two inhibitors we just looked at, one is a direct inhibitor of thymidylate synthase. Again, inhibiting thymidylate synthase reduces production of DTMP, and that's a required nucleotide for DNA synthesis. Alternatively, we could inhibit the folate cycle, and this would also reduce production of DTMP, as this is required as well. So that's where your two inhibitors are coming in. It's also important to note that the folate cycle contributes both carbon and hydrogen to the synthesis of purines as well. So we'll finish this week with this last piece of information, and that's really in the degradation and recycling of purines. So we'll finish this week by looking at the remaining pieces of purine degradation as well as salvage. The key enzymes are listed here, and we'll go through each one of these. The important take-home here is that the end product of this process is uric acid. And I won't spoil this for our next discussion, so I'll leave it at that. And we'll finish with this question regarding methotrexate. So it's a potent anti-cancer agent that starves dividing cells of deoxyribonucleotides through direct inhibition of which of the following processes? So the key to this question is direct inhibition. So we're looking at what is the target of methotrexate. So it doesn't inhibit degradation of purine bases, and we also haven't talked about this. So we can eliminate choice A. So deoxygenation of the ribose ring to produce deoxyribose for DNA. So this is catalyzed by our enzyme ribose nucleotide reductase, and methotrexate is not an inhibitor of that enzyme. So ultimately, the addition of methotrexate reduces the synthesis of thymidine. So that's our end product, but not necessarily our direct inhibition. Our direct inhibition here by methotrexate is by inhibiting the dihydrofolate reductase, which is part of the folate cycle. So our direct inhibition here is of metabolism of folic acid. So keep in mind, if you see a question like this, some of the choices may in fact be true, but if the question is asking for the most direct inhibition route, the best answer here is through the inhibition of folic acid metabolism. All right, we have one short discussion left before we can say we're finished with the course material.